good. I think we're good. All right, so yeah, today we have the pleasure of hosting Yotam Alexander. We'll be presenting his work that was recently accepted to NeurIPS. I'll give the short abstract for this talk. So the title of the paper presented here is What Makes Data Suitable for a Locally Connected Neural Network? A Necessary and Sufficient Condition Based on Quantum Entanglement. And the abstract goes as follows. So the question of what makes a data distribution suitable for deep learning is a fundamental open problem, focusing on locally connected neural networks. We address this problem by adopting theoretical tools from quantum physics. Our main theoretical result states that certain locally connected neural network is capable of accurate prediction over data distribution if and only if the data distribution admits low quantum entanglement under certain canonical partitions of features. As a practical application of this result, we derive preprocessing method for enhancing the suitability of data distributions to locally connected neural networks. Experiments with widespread models over various datasets demonstrate our findings. And we hope that our use of quantum entanglement will encourage further adoption of tools from physics for formally reasoning about the relationship between deep learning and real-world data. So the floor is yours, Yotam.
Thanks. So I'll share the screen. Okay, so thanks for the introduction, Michael, and thanks for having me. Everyone can see the screen, right?
Yes.
Great. So the title of the talk is kind of a zoomed out version of what Michael just presented. So the question that we're interested in is what makes data suitable for deep learning? Now, as you all know, we've been experiencing kind of a deep learning revolution in the past decade or so. These models are achieving incredible results on various data modalities, so image, text, audio, and others. But we also know from theory that there are provable limitations to deep learning. So I can come up with a particular distribution such that no deep model trained by gradient descent will perform well on it. There are, such counterexamples. So this raises the natural question of what is it about natural data that makes it suitable for deep learning? Why is it that these models succeed so well when we know that that's not something we can just take for granted? They do have limitations. Okay, so as Michael mentioned in the introduction, this talk is going to be based on the paper What Makes Data Suitable for a Locally Connected Neural Network, a Necessary and Sufficient Condition Based on Quantum Entanglement. And I should say that this work is joint with two other students, Nimrod de la Vega and Noam Bazin, as well as our advisor, Nadav Cohen. Okay. Now, just an outline of the talk. So first, I'm going to discuss kind of in general the role of data distributions in deep learning. Then I'm going to kind of appeal to an unrelated field, seemingly unrelated, which is quantum physics. Then we're going to give a characterization of data suitable for locally connected neural networks, and we'll conclude. Okay. Oh, I forgot to say from the get-go, feel free to interrupt me with questions or at any time. It's okay. Okay, so just the kind of general statistical learning setup. I'm sure that this isn't new for you, but just so we're all on the same page. So, deep learning is obviously just a particular case of statistical learning. So what is statistical learning? Well, we have an instance space X, we have a label space Y, we have a distribution over pairs of X and Y, which is unknown to us, and we have a loss function from Y cross Y to let's say the non-negative reals. And I see it got garbled a little bit here. So we have the task is that given a training set of M tuples of X's and Y's, drawn IID from D, the unknown distribution, we want to return a hypothesis that minimizes the population loss, so the expected risk over the unknown distribution D. And the approach that we typically take is that we define a predetermined hypothesis space, H, and we just perform ERM, which is to say that we return the H that minimizes the empirical loss. So that's just standard statistical learning. And in terms of the error of the model that we eventually return, it can be decomposed as follows. So we have F star D, which is the ground truth. This is the minimizer of the population loss over all functions from X to Y. which is not a property of the hypothesis set. It's just something that's out there. And the difference between that and H star D, which is the optimal hypothesis from H, is known as the approximation error. And the ability of a hypothesis class to make this quantity small is known as its expressiveness. Then we have a difference between H star D, which is the population, the optimal hypothesis from a population perspective, and H star S, which is the empirically optimal hypothesis, the hypothesis that happens to do optimally well on the data that we drew from the distribution. And the difference between those two hypotheses is known as the estimation error, and the ability of a model to make this quantity small is known as generalization. So the ability to sort of extrapolate to unseen data. And then we also don't have access in general to the sort of ERM hypothesis, the best hypothesis, because we have to perform some sort of optimization to get this. And the difference between the hypothesis that we actually return and the hypothesis that is optimal over the sample is known as the training error. So this is the ability to make this small is a question of optimization, right? And H bar is just the return hypothesis that we actually returned. Okay, so we have all three of these quantities, and for learning to be successful, we need all three quantities to be small. Now, we know empirically that overparameterized deep neural networks trained via gradient descent, they achieve unprecedentedly low population loss. They have incredible results. So that means that, again, all of these three quantities are small. Now, in terms of our understanding of these phenomena, it's fair to say, I think, that it's very partial. So in terms of training error, we do know that gradient descent on large neural networks, on neural networks that are pretty vastly overparameterized, albeit polynomially sized, sort of polynomial factor of overparameterization, they converge to a global minimum, and this is without any assumption on the data distribution. This is known as the NTK regime, if you're familiar, neural tangent kernel. So that sort of deals with low training error, again, in a partial way, because it's not a realistic network, but that's one answer to the question of why the training error is small. As for the approximation error, we know that polynomially sized deep neural networks can express hypotheses with low population loss only for some data distributions, right? So we do have this result, the universal approximation theorem, that tells us that there exist deep neural networks that approximate arbitrary functions, but these neural networks are exponentially sized. So these are very, very far from the deep neural networks that we train in practice. And we know that if you restrict yourself to reasonably sized deep neural networks, then there are distributions on which they will fail to have low approximation error. And the same thing goes for estimation error being small. So gradient descent on deep neural networks leads to optimal population loss only for some data distributions. You can come up with counterexamples. So again, this raises the question of what makes data suitable for deep learning in practice. Why is it that in practice we don't encounter these kind of counterexample-like behavior, and we succeed overwhelmingly with these deep models? Now, why study the suitability of data for deep learning? Well, aside from scientific curiosity, which is, I think, pretty much a sufficient reason in and of itself, a deeper understanding of this issue can lead to methods for either adapting data to neural networks or conversely adapting the neural networks data. Okay, so we're going to focus on the first option in this talk, but the second option is also a possibility for sure. And I think there's kind of a motivation for our study. Okay, so in terms of the sources of error that I described, we're going to focus on expressiveness. So the ability to achieve low approximation error. And we're not going to deal with estimation error or training error. As I said, the training error part is more well understood, I would say. And the estimation error part is definitely not well understood, but this is not the subject of our talk. And in terms of the existing literature on this issue, despite the fact that it's a pretty fundamental question, there isn't a ton of work, relative to this field. This field is kind of exploding, so pretty much everything there's some work. But what we found is that either the existing literature has restrictive sufficient conditions on the data distribution, so Gaussian and stuff that is close to a Gaussian. So right, I can always come up with a sufficient condition that's kind of trivial. If the function that I'm trying to approximate is very easy, then yeah, a deep neural network can approximate it. And I mean, these works are far from trivial, but they do impose strong assumptions on the data distribution. And what we're missing in the literature as we see it is characterizations with necessary and sufficient conditions for low approximation error. Okay. Now I'm going to kind of connect what I just said with a seemingly unrelated scientific discipline, which is quantum physics. I don't know if there are any physicists in the audience, but I'm definitely not going to present like a full physicist-like introduction to quantum physics. I'm not even qualified to give that sort of thing. Just going to give the bare bones from a very computer science perspective. So in terms of the analogy, just to flesh it out, in deep learning, the distribution is given by the data. This is something that's handed to us. And the computational model that we're working with is a deep neural network. Now, in quantum physics, the distribution is given by a particular tensor, and the computational model is just a tensor network. And just to make this a little bit more explicit, if someone is familiar with quantum physics, this may seem a little strange because it's not typically spoken of in terms of tensors, but for me, the tensor is the wave function. The wave function of a multi-body quantum system is just one particular type of tensor. So that's why I'm saying that the distribution is given by a tensor. So now, I know that this is like a tensor network reading group, so I don't really have to introduce tensors or tensor networks, but just to make sure we're all on the same page. So tensors are just multi-dimensional arrays for our purposes. So a scalar is a zero-dimensional tensor, a vector is a one-dimensional tensor, so on. And the edges in a tensor network correspond to contraction. So it's kind of a generalization of matrix multiplication. Okay, so I assume this is all well known. So these are tensor networks. Now, in terms of, just to continue with the analogy, in terms of a theory for the suitability of a distribution to a model, as we mentioned, in deep learning, we currently don't have a satisfactory theory, but we'll show that one can actually come up with a satisfactory theory in the quantum physics setting that's based on quantum entanglement. Okay. So quantum entanglement. What is quantum entanglement? Well, as I said, I'm not going to give like a physics definition of quantum entanglement. It's a very important concept in physics. It sort of, at a high level, quantifies the dependence that a tensor admits under partitions of its axes. And these partitions, in a physics context, would correspond to different parts of the system. So I have a system, how strong are the correlations between different parts of that system? But as I said, in our kind of very formal context, if we have a tensor that is dimension r to the d1 times up to dn, and I is some subset of its indices, then I can always consider the metricization of the tensor t. So I just arrange t as a matrix with axes in I unrolled as rows and axes in I complement unrolled as columns. So I have a tensor and I associate with it a matrix. Now, this matrix, like any matrix, I can always take its SVD, so it's singular value decomposition, and I have a collection of singular values. These are all non-negative numbers. I square them and normalize it, right? So I look at this distribution, which is the normalized squared singular values, and I take the entropy of that distribution. Okay, this operation this gives us what's called the von Neumann entropy, or the quantum entanglement of this tensor, and under this particular metricization. Okay, so this is a fundamental concept for us. Any questions about this?
I have a question here. Is there any condition on your tensor? Like any tensor can fit here, or?
Yeah, so for this definition to work, absolutely any tensor can work, right? Because I just take a tensor, and regardless of what it is, I can always, if I given a subset of its indices, I can form this matrix. And any matrix always has a singular value decomposition. That's one of the kind of the big advantages of SVD, which is that no matter the matrix, no matter if it's a sort of a fat matrix or a tall matrix or whatever its dimensions are, it always has a singular value decomposition. And I can always normalize the singular vectors and compute this entropy. So this will always be well defined. Okay.
Yeah, thanks.
Okay. Sure. Okay. Now we're going to introduce the type of neural net that we have. So we're going to consider locally connected neural networks. So this is a very prevalent family of architectures. So they include convolutional nets, which up until recently were kind of the dominant neural network for computer vision applications. Nowadays, we also have vision transformers, but they're still extremely common. We also have RNNs, recurrent neural networks. So here, the locality aspect is locality in time, right? So we know that the recurrent neural network processes its input one time step at a time. And then we also consider types of local self-attention models. So the kind of general self-attention model has no locality whatsoever, right? So every token attends to every other token. So this is not a locally connected neural network according to our definition, or kind of hand-wavy definition, because I didn't define it formally, but there are for sure variants because this is quadratic, so it's a very expensive operation. There are variants that make the computation local. So you sort of preferentially attend to tokens that are locally next to you. So these are the types of models that we're also considering locally connected. Okay. And now we're going to look at a particular equivalence. So it turns out that this is not a new result in our paper. This is something that was established in previous works, that if you look at a tree tensor network, so in this case, a binary tree tensor network, and let's call it WTN, and you contract it with an outer product of vectors, this is actually provably equivalent to a forward pass of a certain locally connected neural network that is very much like the neural networks that are trained in practice, except that its nonlinearity is multiplicative. So it's kind of like the pooling layer takes a multiplication of the inputs in the sort of convolution window. Okay, so this is and in this tensor network, the bond dimension of the tensor network, which I denoted by R, is equivalent to the number of channels in this local neural network being R. So the width of the neural network is R. Those two parameters match up. Okay. Any questions about this? Okay, so I don't expect you to this isn't obvious, but this is just a well-known fact that there is a particular tensor network that is provably equivalent to a locally connected neural network. Okay. So why should we study these locally connected tensor networks? Well, it turns out that you can train them in practice and they deliver competitive empirical performance, though by no means state of the art. But more importantly for our purposes, the fact that they have this representation as a tensor network makes them tractable for theoretical analyses of expressiveness and implicit regularization in deep learning. So previous works from Nadav's group discuss all these issues as well as other people. Furthermore, these analyses lead to insights and practical tools that can be then applied to more widespread neural networks. So we can prove some results and take inspiration from theory and then apply it to the type of networks that are more prevalent in practice. Okay. Okay, so now I'm going to try to introduce the kind of main theorem that we proved. So to do that, we want to introduce a certain family of partitions. So I'm going to look at the canonical partitions of the subset 1 to n, large n. So what are the canonical partitions? I didn't give a formal definition here, but they're pretty much the sort of the first partitions you think of. So at the 0th layer, the canonical partition just puts everything on one side and nothing on the other side. So it's a trivial partition where everything is on one side of the partition. At layer 1, we just take the first half and the second half of the indices. At the second layer, we take the first quarter, second quarter, third quarter, fourth quarter, and so on. Okay, so I'm going to assume that n is a power of 2 here, just to make it convenient. Okay, so these are the canonical partitions. And it turns out that this question of which tensors can be approximated by a locally connected tensor network, in my terminology, is actually equivalent to having low quantum entanglement under these canonical partitions. Okay, so I'm going to informally state the theorem. So theorem for a tensor A and epsilon, some small constant, there exists a tensor network WTN such that it approximates it in Frobenius distance up to order epsilon, if and only if the quantum entanglement is of order ln of R. where R is the width that I defined previously for all canonical partitions. Okay. Any questions about this theorem statement?
So yes, I have a question. I had a problem understanding it in the paper as well. So here, when you talk about the canonical partitions, it's not every single partition. It's not all the subsets here. It's just
no, it's not all of them.
And what's the motivation to choose like these canonical partitions?
So that's a great question. So the motivation, first off, a lot of the results can be extended to other partitions. So it's not like you absolutely have to use these partitions. But the motivation is we're trying to look at locality in the data. Okay, so these partitions, they form contiguous blocks, right? They're just kind of like the most obvious collection of contiguous blocks, either the entire thing or half the one-dimensional line from 1 to n, or the quarter, so on. And quantum entanglement being low under these is sort of a measure of locality, because all of these blocks, if you look at the boundary, the boundary is always of constant size. So regardless of n, the boundary is always of size 2. So having low quantum entanglement under these partitions is sort of, in a physicist terminology, they would consider it kind of area law-like behavior, because when you look at the quantum entanglement according to these partitions, it's uniformly low, regardless of the size of the canonical partition, because the system only interacts at the edges, and the edges are always of size 2. So you can think of these canonical partitions as kind of like the most local type of partitions, as opposed to, at the other extreme, I could take the partition that is kind of checkerboard. So let's say I would take all the elements from 1 to n, and I'll only take the even elements, and the odd elements would be the complement, right? So this would be a partition where every element is on the boundary. Okay. So a local type of system, you would expect it to have high entanglement according to this partition, because every element is next to an element that is outside of the of its side of the partition, right? So every element 2i is next to 2i minus 1 and 2i plus 1, which are odd. So there's sort of a lot of room for them to interact. So in those cases, there would be less reason to expect the quantum entanglement to be low. So these partitions are sort of meant to convey locality of the system.
Okay.
That answer the question?
Yes,
Thanks.
I see. Thank you.
Thanks.
I have based also. You have a question.
Yeah. Okay.
Yeah, thanks, Guillaume. Yeah, I have a question. So as you said, I is the rows of our matrixization of our tensor, and then we partition the rows of the tensor, the rows of the matrix. But I didn't understand that why it is canonical and how you partition these rows. It's not obvious for me.
So canonical is not like meant as a mathematical formal definition. I'm not saying that every single person would agree that these are the most important partitions. It's just a name. I'm not claiming it's canonical like in the mathematical sense that. I'm sorry if that's misleading here. I'm not claiming that these are the only partitions that you would consider, or that there's some kind of mathematical universal criteria that would single out these partitions. I'm just saying that if I have indices of the tensor 1 to n, that this is a family of partitions. The reason we call them canonical is just because these are kind of everything all the theorems can be phrased only in terms of these, and it's a result that it's sufficient to only consider these types of partitions.
Okay, thanks.
Sure. Was there was another question, I think?
Yeah, I have a quick question on here the WTN. So you said there exists a W which is parameterized by a tensor network. What is the structure of this W? This I didn't get really.
So W is just a binary tree tensor network of width R. Okay, so a lot of these results can be extended to, and there's also an extension in the paper, so it's a good question to sort of bring up. There's also extension in the paper to a multi-dimensional case of where this is all in 1D, right? So 1 to n is like is elements of the line. So I can also extend it to multi-dimensional, and I can also have different bond dimensions. But the simplest kind of statement of the theorem is just for a binary tree tensor network. Okay.
Yeah, that makes sense. Yeah, so actually these canonical partitions kind of come from the tree tensor network structure that you
exactly.
So if you would consider another family, you would have other kind of partitions to consider. Yeah,
exactly. This is in my next slide, actually. Yeah. So just kind of an intuition for the proof. One intuition is the thing that I sort of hand wavy gave about locality, but the more kind of mathematically grounded intuition comes from the fact that in a tensor network, I'm not sure what exactly the background is for people, but I think it's pretty intuitive that that the amount of entanglement that the tensor network can represent is given by the min cut of the graph of the tensor network. It's proportional, logarithmically proportional to the min cut of the graph. So if I have two subsets of my tensor network, and I look at the graph that the tensor network has, and I cut this graph, that this is actually the number of edges that crosses this graph, take the logarithm of that, that's proportional to how much entanglement this tensor network can represent. Okay, so this is why, for instance, in our case, this is why it's natural to consider these canonical partitions, because these are precisely the partitions that have a single edge can cut them, according to if you look at the binary tree. So this is why this particular family of tensor networks is particularly constrained in having high entanglement across these partitions. So this is maybe even a better motivation for why we consider canonical partitions. Every single one of them can represent only order of logarithm of r, ln of r, entanglement across this partition. So this constrains my tensor that I'm trying to approximate. So basically, the statement is in one direction is that if I'm trying to approximate one tensor by a different tensor, I better have approximately the same level of entanglement across really any partition, but in particular for these type of partitions where I'm particularly constrained. So in this cases, this gives me the strongest constraint on how much entanglement I can have in my tensor, and only have order of ln r. And then the other direction is showing that this is actually sufficient, so that if I have this about this amount of entanglement, then I can also totally reconstruct the tensor. But this is a non-trivial statement, but this is the statement of the theorem. Okay. Okay, hopefully that gives some intuition for the proof. Okay, so far I've described something that is purely in terms of approximation of tensors, right? Nothing to do with learning or machine learning or anything like that. So how does this relate to learning? So what is our setting? So suppose I have a training set S of m data points, where each one of these tokens is a xm is a d-dimensional vector, and they're all normalized. So their norm is smaller or equal to 1. And I'm considering binary classification, right? So what the y's are all 1 or minus 1. And the classification problem I'm trying to learn is I'm trying to learn the parameters of a locally connected tensor network via softmax SVM objective. So this is a standard loss in machine learning. I have the maximum of 0 and 1 minus the predicted label times the actual label. Okay, and I'm constraining my my tensors to have norm at most 1. So it turns out that under these settings, in this case, minimizing this loss is actually just completely equivalent algebraically to minimizing this expression. So 1 minus the inner product between this tensor and my W tensor, WTN. Okay, so this is what leads us to define maybe kind of the main definition of the paper, which is the empirical data tensor. Okay, so the empirical data tensor of any distribution, regardless of where it came from, is just given by the following expression. I take the outer product of all my feature vectors. So each one of these xm's, you can think of them as like the elements, like the tokens of a word. So each one of them is like some dimensional vector, like a 4-dimensional vector or something. And I'm taking the outer product of all of these for each one of my samples, multiplying by the label, and then averaging over the entire data set. Okay, so hopefully we all agree that this is some tensor. Okay, and it turns out that because of this algebraic manipulation that I just showed you here, that minimizing the loss is really just equivalent to approximating this tensor. So I get low population loss, low training loss, sorry, if and only if the distance in Frobenius norm between the normalized versions, this normalization is a technical point, it's not so important, but basically if and only if I can approximate this empirical data tensor. Okay, any questions about this definition? Okay, and so what this means is achievable accuracy over the training set is determined just by this approximation problem, approximating the empirical data tensor with a tensor network from my family of tensor networks. And you can make the exact same argument if you look at the population loss, and we can show that if you replace the empirical data tensor with its population analog, so just the expected value, the expectation over basically the empirical, or considered differently, the expectation of y times this outer product over d, then the achievable test accuracy is determined by my ability to approximate this tensor. So this is called the population data tensor. Okay, so we define the suboptimality in achievable accuracy as this minimum, as the best approximation I can get to the population data tensor. Okay, so this quantity actually determines how well I do in terms of my approximation error. Okay, now okay, so we now saw that we can reduce this particular machine learning setting just into a question of approximating two tensors, and now we are immediately led back to our previous theorem, which says precisely that to approximate some tensor A up to epsilon, I need precisely that the quantum entanglement of A is of order ln R for all canonical partitions, and we get an immediate corollary. I can get this suboptimality gap to be small if and only if the entanglement of the population data tensor is small for all canonical partitions. Okay, so that's just an immediate corollary of the theorem once I've shown that this is the form that my population loss takes. Okay, so to sum up, accurate prediction is possible if and only if the data distribution admits low entanglement under canonical partitions of the features. Remember that the data tensor, it's this outer product of features. So ultimately, the canonical partitions are partitions over features. Okay, so accurate prediction is possible if and only if the data distribution admits low entanglement. Okay, now two questions are kind of raised themselves. So this population data tensor is of exponential size, right? So if each feature is of size, let's say 2, then the size of this tensor is 2 to the n, right? So it's a huge tensor. I can't compute its quantum entanglement in a naive way because I can't even store it. It's way too large of a tensor. And furthermore, I don't even have access to the population data tensor, right? I only have access to samples. So two statements. First off, we can use kind of standard, basically generalizations of Hofting's inequality to Hilbert spaces to show that the population data tensor, the quantum entanglement concentrates. So I can approximate the population data tensor with the empirical data tensor. And also, this doesn't help us with the problem of computation, right? Because they're both the same size. They're both of exponential size. So there's another trick that allows us to actually compute these quantum entanglements efficiently. Okay, so the bottom line is this sufficient and necessary condition can be evaluated efficiently. Okay, and just to give kind of a flavor, because I think it's kind of a cute statement or cute proof. So for a general tensor, I wouldn't be able to compute this entanglement, right? The reason I can compute this entanglement is precisely because this tensor is given by a sum of m samples. Okay, so I'm going to get something polynomial in m. So how do I do this? Well, just at the high level, I'm not going to go through the exact algorithm, but the main point is that if on both sides of the partition the vectors that I had were orthonormal, then I could just read out the coefficients immediately. But the fact that they're not orthonormal means that I have to do a Gram-Schmidt basically. So there's a kind of orthogonalization process that I can do to compute the entanglement of this empirical data tensor, despite the fact that it's of exponential size. So I certainly can't naively just load it on a computer and run SVD. Okay, so this is it's an interesting kind of trick, but I'm not going to go into the exact details of how it works. Okay, so as we said, overall, we have theoretically that the suboptimal is less or equal to epsilon if and only if the quantum entanglement is of order ln R for all canonical partitions. So now let's look at a bit of a kind of empirical kind of sanity check for our theory. So what we did is we looked at a standard kind of audio data set, and we started swapping the features. Okay, so we saw how both the quantum entanglement increases as we do more of these swaps, and the accuracy of these locally connected models. So a CNN, I think it was called M5 CNN, the S4 RNN, and the local attention model, how both the quantum entanglement goes up and the accuracy goes down. So the more heuristically over this data set, the more entanglement we have, the worse we are in terms of classification. And so that's kind of a sanity check. So the performance of locally connected neural networks is inversely correlated with entanglements under canonical partitions of feature and data. Okay. So
sorry, I have a
I
have a question about the swapping the features. What do you mean exactly? Because so the features have an order and just swap them.
Yeah, we have this audio data set, right? So every data point is like I think it's 16,000 like tokens of audio, and I literally just swap these tokens. So I get something that's completely garbled, right? I take a regular audio and I swap and I randomly swap more and more of the tokens of the audio, and I sort of break the structure of the audio, right? So it's not surprising at all that the performance of goes down, right? Because of course something like a CNN or an RNN, they're meant to use the original structure of the data. If I permute the order of the audio, then of course the performance is going to go down. But what's a little bit more interesting to see is that the quantum entanglement goes up. So intuitively, what that means is like I'm sort of breaking the locality of the data, and this notion of canonical partitions and quantum entanglement is detecting it. So I'm getting more entanglement because the data is less local, because I'm breaking the local order. The data has this natural local ordering of speech in this case, and I'm breaking it to a larger and larger extent because I'm doing more and more of these swaps. Does that answer the question?
Yeah,
Thanks. Okay, so theory suggests that data is suitable for a locally connected neural network if and only if it admits low entanglement under canonical partitions of the features. And this raises the question of, can we enhance the suitability of data to a locally connected neural network by rearranging the features such that this actually holds, such that we lower the entanglement under canonical partitions? Okay, so you can think of it as like a pre-processing or maybe kind of a particular type of representation learning. In this case, the representation we're learning is just a permutation, but still we're trying to rearrange the data so that this theoretical condition holds. Okay. So what did we do? We did kind of the most obvious thing. I called it a greedy coarse to fine search for feature arrangement. What does that mean? So we look at all of the features, and this is like we think of this as 1D. So we have a block of features, and I'm looking for a balanced partition with minimum entanglement. So completely ignoring for a second the computational aspects, I'm looking for a balanced partition, so a partition into two sides of equal size, such that the entanglement is the minimum possible. And I'm going to turn this into my canonical partition. So I'm going just to put one side of this partition, I'm going to rearrange the data such that one side of this partition is on the left and the other side is on the right. So this applies a permutation to my data. And then I'm just going to recursively do this on both halves of the data. So after I do that, I recursively do the same thing on both halves. Okay, so I managed to find two halves of the previous halves and so on. Okay, so after all of these steps, I've learned some permutation of the features, where I've constructed the permutation such that the quantum entanglement under canonical partitions is minimal. Okay, and ultimately I get a new feature indices. So in this case, 1 to 16, that are a rearrangement of my original features. And so this is, again, completely ignoring the computational aspects. But the problem is that finding this balanced partition minimizing entanglement is computationally prohibitive. So it's an NP-hard kind of unstructured search problem. And it was hard for us to do this on large dimensional data, high dimensional data. So what we ultimately did in the paper is we replaced quantum entanglement with a kind of what we call surrogate entanglement, which is a pairwise measure based on Pearson correlation. I didn't give the exact formula; it's not so important for our purposes. But the upshot is that we can reduce this balanced partition with minimum entanglement problem into a minimum balanced cut problem on a graph. And this is also an NP-hard problem, but it turns out that there are a lot of great approximation algorithms for this problem. So you can actually do this for graphs of size, so number of features of size tens of thousands. Okay, so you can actually perform this much more efficiently in practice. Okay, So this is kind of our application. This is what we actually did to the data. So just to be sure. Yeah.
So here I didn't get why is so basically computing the Pearson correlation. Okay, computing the Pearson correlation, you compute it between pair of variables, and then you have your graph like this, and then you're looking for mean graph. Whereas if you were to do that for the entanglement, because you said you have a polynomial time algorithm to compute.
No. It's a polynomial time algorithm, but this problem is still NP hard. Okay, so the reason I couldn't do this for the entanglement is that it's not defined pairwise. It's defined only for subsets, right? So there is no graph, natural graph that I can associate to it.
Okay, so you would have to estimate the quantum entanglement for every possible binary partition of your features. This is the
Exactly. Okay. This is the bottleneck, but this is not a theoretical statement, right? So this problem, unfortunately, it's still NP hard, and it's also NP hard to approximate. Ultimately, we're using a heuristic algorithm. It just turns out that there are very good heuristic algorithms there. It's called there's one known as Métis. It's based on something called graph partitioning. It turns out to work very well for our purposes, but it's not that there is ultimately like a polynomial algorithm with guarantees for these problems.
Yeah, I see. Okay, thanks.
Sure. It just turned out in practice it was much easier to do. Okay. So this is the algorithm. So I'm not, again, the pseudocode is not so important, but ultimately we just we take an input this data and we output the permutation, and the way we do this is that we recursively take half of the data and to take to the right half and to the left half the partition that approximately minimizes this surrogate entanglement, so not the original entanglement. Okay, and approximately solving is where I'm exactly addressing the question from before. This is not a rigorous algorithm that we can provably say that it minimizes this thing with guarantees. Okay, so empirical evaluation. So for two different types of data. So what we'll show here is that this type of approach improves the performance of these locally connected networks on two types of different data sets. So one type of data set is this permuted audio. So I permute audio, which of course hurts the performance, and then I try to reconstruct the original order using this heuristic based on entanglement, and we show that we can improve the performance. And also, this was our original motivation, we wanted to improve the performance on tabular data. So tabular data is data that by definition, I don't have any sort of local structure, right? And so we want to discover such structure. That's kind of our high level goal. And we showed that we can improve the performance of these locally connected networks on a bunch of tabular data sets. 3 of them are given here. We weren't able to get to state of the art on these things, but we did improve the performance. Okay, so we think our method renders locally connected neural networks, which typically perform very poorly on these tabular data sets, precisely because they don't have any local structure. We think they're viable for tabular data, and this is important in high dimensional settings, right? In a low dimensional setting, there's no particular reason for me to use a convent. I can just use an MLP, or I mean, there are other methods too, XGBoost, all sorts of stuff that you can do for tabular data. But in particular, there's no reason for me to use a locally connected network. I can just brute force it using an MLP. But in high dimensional settings, we might have to somehow constrain our number of parameters using locality. Okay. So to recap, over-parameterized deep neural networks trained via gradient descent yield unprecedentedly low population loss. It's really incredible what these models can do. And we show that, or we discussed how this ability to have low approximation error and low estimation error relies on properties of the data distribution. It's not a statement that I can make for every data distribution agnostically, just make the statement. So this leads us to the question of what is it about data distributions that we encounter in practice, which leads these algorithms to perform so well. And we showed that in theory, we have a particular model, a particularly locally connected architecture, such that accurate prediction is possible if and only if the data admits low entanglement under canonical partitions. And we gave a practical application, which is we try to enhance the suitability of data to locally connected networks via this feature rearrangement algorithm that I described. Okay. And we did all of this using tools from quantum physics. And just to kind of give a high-level, more philosophical takeaway, so deep learning is most commonly applied to data modalities regarded as natural, some sort of natural process generated them, images, audio, text, etc. But this is difficult to formalize. It's very easy to say, kind of in a kind of a hand-wavy level, that convolutions use the locality of structure, right? This is something that people have been saying for 30 years, right? But if you try to formally prove something, it's very hard to come up with a necessary and sufficient condition of these distributions that makes them local, because this is kind of a slippery concept. And we think that we can overcome this difficulty to formalize, to sort of reason about natural data using tools from physics. This is our hypothesis, that physics can give us tools to reason about natural data. That's it. Thank you very much. Okay.
Thank you so much. If anybody else has any other questions, we still have another 10 minutes.
I have a quick question. Go ahead, Father.
Okay, I will ask first, if you don't mind. So I have a very general question. It's about all of these works that you have in the previous works on entanglement entropy. They're all about a subset and the complement of that subset, which covers the whole, like all the features. What if we are interested in just two subsets, not which is not, they're not complement? Is it possible to do so?
So that's a great question. So it's in general possible to do it, but it's harder, because even in physics, you first want to marginalize on all the elements or features that you're not interested in, and then only consider A and B, right? So we actually thought about this during the work, and we're considering doing something like this. So in physics, what you can do, right, is that if you have one quantum system and you want to marginalize on some of the degrees of freedom, you get a density matrix, right? You get and then you can consider the entanglement of this density matrix. But it turns out that, and I'm not a physicist, so I'm just giving kind of my impression, that things become much more complicated if you want to use these particular entanglement measures. So there are a lot of different measures of entanglement for density matrices, and it turns out to be much trickier to do. So we thought about doing this, but it's definitely a kind of a limitation of the formalism. It's much more natural to deal with these one system and its complement and dealing with two subsystems.
Yeah. So, and marginalization is not easy as well, right?
It's not as easy as you would think. So you could just do it, right? And in our setting, you could just ignore all the features other than the ones in the two sets that you are considering. But that would break the theoretical guarantees. So I could always just look at let's say I have A, B, and C, and I want to marginalize over C. I look at the outer product only of the elements of A and B, and just build this tensor, and then consider its entanglement. I could compute it, but it would break the theoretical guarantees.
I see. Thanks.
Sure.
So just which guarantee will it break?
So the necessary and sufficient conditions for approximation.
Okay, I see.
So I'm actually not sure how to generalize the theory part to a case where we're considering non-exhaustive subsets.
Mm-hmm. Yeah, I see. That makes sense. So just for like your first theorem, right, the approximation, where you say basically you need to satisfy this low entanglement entropy with the cuts that are the one edge cut in the tensor network.
Yeah,
makes sense.
Yeah.
Okay.
I don't know how to say anything really about even just one non-exhaustive partition or non-partition. I'm not sure how to say theoretically.
Yeah, that's interesting. I had a question about, can you give us a little, I don't know if there are other questions before, but mine is maybe a little bit technical, but just, so go on your entanglement computation.
Yeah.
Can you give us some little insight about how that works?
Yeah, so first off, it's not original to us. The trick, it's a nice trick, but it's really just kind of a linear algebra thing. I think it's well known to physicists to work with tensor networks. It would be well known to them. So imagine that I have it's XA and XB, right? Let's abstract from how I got these XA and XB, and I want to compute the entanglement. So if all the XA vectors and all the XB vectors were mutually orthonormal, it would work. I would just read off the coefficients, and this would be the Schmidt decomposition, right?
Yeah.
So so all I have to do is move to a basis of orthonormal vectors, right?
Yeah.
So to move to a basis, all I have to do is compute the inner products between these XA vectors and these XB vectors, between them and themselves. Because all the Gram-Schmidt decomposition, which takes me vectors and turns them into an orthonormal basis, it only relies on inner products.
Mm-hmm.
That's all I ever need to compute. So because I can't compute these inner products in polynomial time, these are just products of features. So I can compute the inner products efficiently. I can move to this orthonormal basis and then compute it.
Okay.
So this is despite the fact that I'm working in an exponential basis, exponential Hilbert space.
Mm-hmm. And I think somehow, I don't know if you know, like there's this TT rounding algorithm where basically you take a tensor network in a tensor train format and you're able to compute its SVD just by doing QR decomposition and pushing them around. I think what you're doing is very similar to that, because you're starting with a CP tensor and then you're doing some local QR basically with this gram sheet that you're pushing. But I'm still didn't figure out how do you do the pushing around. But I think it's in the same spirit as this, right?
I'm 100% sure that this is something that was already known, and physicists were already doing it without using the exact same terminology, but they were computing these entanglements.
Thank you.
Sure.
Yeah, go ahead, Bruno.
Hi. Thanks for a wonderful talk. It was very interesting. Going beyond what you presented, I was wondering, what if you do have entanglement in your data?
Yeah.
Is there a golden path to still do something with deep learning? I think some of the images you've shown were basically, small world networks, which got me thinking, well, could graph neural networks help? Is there?
So what?
Go ahead.
Sure. Do you want to finish? Sorry.
Are we just helpless if the data sets do have entanglement, or is there a preferred way of trying to get away from very local CNN-like things?
Yeah, so in terms of the graph neural networks, there's actually a follow-up paper, or I shouldn't say follow-up because they were kind of independent, but there is actually a paper from Nadav's group about graph neural networks that also uses that considers this problem, how to kind of optimize graph neural networks for data that is highly entangled. Sorry, it doesn't use exactly the same formalism, but it really deals with this problem that you're mentioning. In terms of what if the data is extremely entangled? So in theory, it's hard to say things. Of course, that doesn't mean that in practice the methods won't work. There's a billion different reasons why a theoretician would tell you that deep neural networks are not going to work. There's so many different reasons. You're solving a huge non-convex problem with gradient descent, and the model is over-parameterized. And there's so many reasons, but yet it works, right? So I'm definitely not going to say that in practice, if the data is highly entangled, it's not going to work. One interesting thing is that we considered the point of the application, right, is to find a representation that has low entanglement. But we only looked at a very simple type of representation. It's just rearranging the features, right? There's nothing that's telling me that I can't do a nonlinear transformation of the features that reduces entanglement much more. But this was just harder for us to do, and in practice, we couldn't get something to work better than the feature rearrangement. So we just stuck with the feature rearrangement. But for sure, you could think of, okay, what if I try to learn a different type of representation? That say I try to, let's say, lose as little information as possible, so something like an autoencoder, but also have low entanglement. So to use it kind of as a regularizer term. There are a million different types of regularizer terms that people use for autoencoders. So maybe this could be a different one. So an autoencoder that tries to have as little entanglement as possible between features. But in terms of your sort of overall question, for sure, in practice, I think these networks can work also in cases where there's high entanglement. It's not like a deal breaker in practice, but it's very hard in theory to reason about why they work.
Thank you.
Sure.
So if there are no other, yeah, I had to go ahead.
I was about to say that. Yeah, if there's no other questions, then I guess we can finish for today. Thank you again, Yotam, for the great talk.
Yeah, thank you, Yotam. It was really, really interesting. Cool work.
I'll stop the recording, and hopefully it's going to be posted soon.
Yes.
Sure, thanks for having me.
Yeah, thanks so much. Have a good day, everyone.
Thank you.
Bye.
Bye.